So now we look at a few examples and where we learn how to apply Newton's second law to rotating or revolving systems. Let's consider a 65 kilogram boy sitting 1.5 meters from the center of a merry-go-round. The ride completes 1 revolution in 2.5 seconds. How much centripetal force is acting on the boy? Assume he doesn't go flying off. So here we have a top view of that child sort of riding around. And so remember, they are traveling this way. That would be their tangential velocity. And they are accelerating inward, right? So we have these two vectors that are occurring here, tangential velocity and acceleration. Now remember, acceleration requires forces. So if we look at an FBD on the side view, we would see that, let's see, the Earth is pulling them down. The merry-go-round itself is holding them upward, so the normal force and the weight force, those two forces are acting, they are balanced. They are not centripetal forces. There is a centripetal force, and that force is pointed inward. Okay, and so we could call that, in general, we could call it F sub C, but in reality, I'd like to know the type of force that is. And you can tell by looking at this, the person's not holding on to anything. They're sitting here. That would actually be static friction that's holding them in place. So let's see, we want to determine the magnitude of that centripetal force, so we of course use Newton's second law for that. We're going to make those centripetal forces. I see that there's only one force that's centripetal. There's only one force that's unbalanced. That would be the static frictional force, is equal to m, let's see, based on what I'm given up here, 1 revolution in 2.5 seconds. That means I'm going to go ahead and use this equation, 4 pi squared r over t squared. And since I'm just looking for the magnitude of that force, that'd be 65 kilograms times 4 pi squared. I see the radius is 1.5 meters, so 1.50 meters. And I divide that by the period. Now the period, 1 revolution in 2.5 seconds. The period is 2.5 seconds there. That's how long it takes to complete 1 revolution. And so let's see, that's squared. And now I can go ahead and compute that. And that value turns out to be about 616 newtons. And that is, of course, supplied by static friction. And you may recall, static friction can only grow so high. If I spin faster than static friction would be able to supply that force, I would end up sliding right off of that thing. Now, a 210-gram ball revolved horizontally at the end of a 1.3 meter string completes 2 revolutions in 1 second. What's the magnitude of the centripetal force acting on the ball, and what creates that force? Well, let's draw a quick FBD here. We have the weight of that ball, and we have a tension force. Now, that tension force, I know it says here that it's being revolved horizontally. Let's just consider what that would look like. If I were to draw that like so, and I said that the tension force was horizontal, first thing I can see is that there's no way that this could actually stay in a horizontal plane. The unbalanced force from the weight doesn't have anything that's holding it upward. This thing would tend to accelerate not just inward, right, towards t, but it would also accelerate downward because we have an unbalanced weight here. So in reality, I cannot actually have this thing in a horizontal plane. It cannot work like that. There has to be some vertical component of that tension force. I'm going to go ahead and draw that like so. It's going to end up being quite large in order for that to balance that weight, and I'm going to go ahead and draw that using components. This force here, which I might call tension in the y, must balance the weight of that object in order for it to be in equilibrium vertically. So I simply cannot have a horizontal rope there. It's got to have some angle to it. Now what I'm looking for is the unbalanced force, is this right here. This T sub x, all right, the horizontal component of that tension force really is my center seeking force. So if I want to determine what the magnitude of that is, I'm going to use Newton's second law. I see that it's just the horizontal component of the tension force. Since I'm giving, again, 2 revolutions in 1 second, I'm going to use the 4 pi squared r over t squared. And let's see, the tension in the x direction, 210 grams would be 0.21 kilograms, 0.210 kilograms. times 4 pi squared times the radius. In that case, the radius would be, looks like about 1.3 meters. And then I divide that by the period squared. Well, if it takes 1 second to complete 2 revolutions, then it would take half a second to complete 1 revolution. So the period would be half a second. And so now we can go ahead and calculate the value of that center-seeking force. And that would be in the neighborhood of about 43 newtons.